So this video is going to be about how to solve this monster of a function using the chain rule, and the aim is going to be to teach about extended usage of the chain rule past just one u substitution. And it's kind of cool because you'll be seeing how the chains will link up and how the notation, for example, dy over du times du over dx, you can kind of see how the notation will work out in a way that they cancel out like fractions, even though that's not really what's happening, but you can assume it works like that for now. So first I'm going to call this my y. I'm gonna rewrite it because in trig functions you put the squared here, because if you put it here it's confusing as to whether it's this being squared or the entire thing being squared. I'm gonna write it in brackets here. Tangent of the square root of ln 1 plus sine 2x. I'm going to close the bracket and square it. And now here we begin defining terms for our chain rule. So what we're aiming to do is to simplify this function down, and through a multiplication of the derivatives of every single segment of this function, then we can find the derivative of the outside function. So this entire part here is being squared. That's our outside function. So I'm going to call this equal to u squared. You see these? And you can see this pink underlined part, the entire function here. So tangent and everything that's within this tangent. I'm going to call it u. Then I'm going to define u as the tangent of the square root of exactly what's above there, just without the squared now, plus sine 2x. And now our next stop in the function, we have an entire part here that's within the tangent function, this entire square root function. So I'm going to call this the tangent of, and the pink part is t, right? And then I'm going to call t the square root of ln 1 plus sine 2x. And of course, the square root is now our outside function, and everything within the square root is going to be our next letter, which is s. And then s is going to be equal to ln 1 plus sine 2x, because that's what we got from up there. Now we have the natural log as our outside function and something within it. So, of course, we're going to call this the natural log of, let's say, r. R should be in pink. And we're going to call r 1 plus sine 2x. But oh wait, now we have a constant outside the function. What are we going to do? We're just going to include that in our definition. So r can be defined as 1 plus sine of, and let's call 2x our next inside function, q. And finally, q will be equal to 2x. And there's nothing left to tack on, because what we're trying to do is derive all the way from y to x. And we're going to have to get through all these variables. So the principle of chain rule is that the multiplication of all the derivatives, starting from the outside inwards, as a result of taking the derivative of both sides, for example, and having it within an outer function, by taking the derivative of both sides and plugging in your function again and again, you'll eventually get the original function through the multiplication of all these chains. So if we were to write out what we had up here, multiplying the derivative of y u t s r q, it would be either of these forms. So either. These are just two different notations. In this upper form here, there's a nice way of thinking about it where the fractions maybe cancel out. You can't really say that, but that's kind of what it looks like, and you'll end up with dy dx. This is what we're doing with the functions. We're multiplying all the derivatives together, and we'll end up with the original function's derivative. So I'm going to start doing this. It's going to take a little bit. So in order to start deriving, we're going to take the derivative of all these functions here. I've helped you guys out and shrunk it down and put it to the side so we actually know what we're looking at when we start deriving. So we just need to multiply the derivative of all of these, and we will find the entire derivative. So first we need to find dy du, and that's going to be equal to 2u. Based on the power rule, this is 2u to the 1, but let's write it as 2u. Then we need to find du of dt, and you can see how this is the output variable and the input variable as we kept substituting deeper and deeper down the chain. That's why we have the y up here and the u out here. Normally when we have some kind of like y equals blah blah x, then the derivative of that is going to be dy dx, where the y is the output variable, or the dependent variable, if you want to think of it like that. So du by dt, tangent of t, so that's just going to be secant squared t. It's just the same as 1 over cosine squared t. This is the way I'm going to write it. It's going to be nice and neat later. We're going to find dt by ds. And I'm going to show you the shortcut for a square root. It's going to be 1 over 2 times the square root of whatever was inside. And the reasoning for this is if we have some variable, let's say a square root, and we're trying to derive this, okay, so it'd be dA. Then this is the same as the derivative of a to the 1/2. We're going to subtract 1/2 from 1 from 1/2, and that's going to be a to the negative 1/2. And we need to move the power to the front. That's going to be 1/2 times. So that's just going to be 1 over 2 and the square root of the thing we had. So that's the shortcut for all square roots. Should work fine. Then we're going to have ds by dr. Natural logarithm of r, that's just 1 over r. And then we have dr by dq. As we keep going down the chain, we find the derivative of 1 plus sine q, and the 1 goes to 0. Sine is cosine of q. And then finally, we have to multiply by dq by dx, and you see we went all the way from y back down to x, and that's going to be just 2. So now we're going to need to multiply all these terms together. But you'll notice we still have variables from each of the steps. Like for example, in the step for u, we have t, and t we actually know the value of. We know the value of everything. So actually our entire thing is solved right here. So 2 times u, and we know what u is. U is right here. So 2 times tangent of the natural log of 1 plus sine 2x. Sorry, this is going to take a while. Then we have to multiply by secant squared of t. So secant squared of whatever t is, which is the square root of natural log 1 plus sine 2x. And then we're going to multiply it by 1 over 2 times the square root of whatever s was, which is the natural log of 1 plus sine 2x. Then I'm going to keep multiplying on the next row. We have to multiply by 1 over r, and r is just 1 plus sine 2x. 1 plus sine 2x. Then we're going to multiply by cosine, dr dq, which is cosine of q. So cosine of whatever q was, which is just 2x. Then finally multiplied by 2. So, well, you could go through all the trouble of simplifying this, but this is your answer. I also plugged it into Symbolab just so I could prove it. If you simplified it out, this should be what it looks like. Let's see. There's the little part here and the part here. Let's check our denominators, see if it's similar. So this was the denominator here, because this goes, this one here and this one here. And yep, it looks to be the same answer in the end. So yep, that's how I would approach this question. You could probably have this in a few less chains if you use the natural logarithm rule and split. Oh, sorry. You couldn't because this is not the multiplication of two things, but rather an addition. So this is probably the least amount of chains you could get it in. But yeah, this is how you do it for this question. And this is hopefully serves as a nice introduction to the chain rule for when there are more than just two functions nested.